At the end of the lesson, you are expected to identify the process of solving a constrained quadratic optimization, analyze the process of solving the constrained quadratic optimization problem, and appreciate the significance of processing the mathematics of support vector regression. Relying on this very fundamental concept about support vector regression may not always give us the best optimized model. The reason for that is even if this part can give us a feasible convex problem, but in situations where we allow errors, this particular instance can never give us the proper output. And so to solve this kind of problem in this situation, we have added the slack variables. But then, even if with the introduction of the slack variables and the use of constant, we may not still be able to properly optimize the result of our model. The reason is that is the result of the use of this parameter may not be able to give us a smooth result because when the value given by a data scientist to see is very much big, there will always be a tendency of overshooting, and this overshooting may not be able to give us the proper minima that can be used for our modeling. So with that, today, what we're going to do is we're going to solve this problem of constrained quadratic optimization. Before we continue, please don't forget to click the subscribe button down there because we do have a lot of exciting free data science lessons for all of you. We do have mastering machine learning algorithm, the deep learning mathematics, the different data science algorithms, and a lot more. And don't forget to hit the notification icon so that you will be able to get notification every time we upload a new video. And don't forget to give this video a thumbs up and share this with your friend. So let's continue with our lesson. For us to solve the problem of constrained quadratic optimization, what we're going to do is that we're going to find the Lagrangian of our equation. So now here, what we will do is that we are going to use the Lagrangian multipliers. Let me write here first. So this Lagrangian can help us find the remedy to the problem we have just stated. We have what we call Lagrangian multipliers, and this is also called dual variables. This is called dual variables. It's because we're going to use two variables. So we have the first one is represented by lambda, and the second one is represented by alpha. And of course, when we say these two variables, we always have to consider the upper and the lower part of our hyperplane. So we have discussed about that one. We have differentiated the different parts of our hyperplane. And I believe as of this moment, it is easier for you to really understand what I'm talking. And if you haven't yet understood what I'm talking, please, I suggest you study from the very start of this playlist so that you would be able to understand this one and the hyperplane that I'm talking and the upper and the lower part that I'm also talking. So using our Lagrangian multipliers, we have obtained this kind of presentation of our new model. And of course, we have retained our basic optimization part, and we add the non-negative Lagrange multipliers to our constraints. So of course, our first constraint is this one and this one. Maybe you would like to ask me, what is this kind of constraint that you are talking? So let's have this one first before we move on to more understanding of this equation. Let's first have this one. The constraint here is that the product of our Lagrange multipliers is 0. So for the first one, we have the alpha I, that is for the upper part of our hyperplane. It is 0. And for the lower one, it is also equal to 0. And of course, with respect to lambda, the situation is still the same. And that is, it is also equal to 0 for the upper one. And for the lower one, it is also equal to 0. But then, of course, we are considering here simplicity. And when we speak of simplicity, we do not actually use all of the vectors, but we only select those support vector that are very crucial in our optimization or improved optimization. And so this is what we call solution sparsity. and this is written as this one, right? I hope everybody is following me. So let's go back for a while to this one. So we have here our first constraint for the alpha, which is below, and for another alpha. And of course, we do have another constraint for our lambdas. But of course, what we're trying to do is that we would like to take small steps to get to the minimum of our data points. So if you could still remember in our lessons about gradient descent, we talked about the global minima and the local minima. So the same situation is also applicable with respect to understanding and identifying the local and the global minima. But here in our case, what we are trying to get is the local minima. Say, for example, we do have here lots of points. And what we would like to do is that we would like to go to the local minima. Let's just take this one as our local minima. And our consideration is that we don't want to get to this very part of our data too much fast. It's because when we do it very fast, that is by taking very big steps, then there would be a tendency of overshooting, and our movement would be something like this. And we don't want to go to this kind of situation. And what we would like to do is that in as much as possible, we're going to go to a very smooth course of our journey. We will do maybe something like this. So this would be the kind of journey that we would like to take. So as you could see, there would be a difference in the curve. And for us to be able to do this kind of process of taking small steps, what we will do is that we're going to find the partial derivatives. If we are going to take the partial derivatives of the variables with respect to the Lagrange, we are still going to return to the constraints, which could be less than or equal to 0. And that is for both alphas. So understanding these constraints, understanding this Lagrange, then what we will get is a brand new function approximation, which is described by this mathematical formulation. So this part talks about the constraints. This one talks about the W, which is the dot product of the different data points. So taking into consideration all of these things, this function, the Lagrange multipliers, the partial derivative, then we can arrive at this dual form of our optimization problem. And so this is now our new form, which is subject to this constraint. What is this for? Why do we have to study this? We have to remember that we use an objective function. With this, we have to tune it for the optimal performance of our model. And the process that we have discussed shows us how to do it. After all being said and done, let's try this. How is the constrained quadratic optimization problem solved? How is the minimum of the equation found? Please write your answers in the comment down below so that we would be able to have a very rich interaction of ideas and we can learn from each other. Do you want to know more about this channel? Just click these cards. You can enjoy our data science courses for free, like mastering machine learning algorithm, deep learning mathematics, the different data science algorithms, and many more. Learn and upskill for free.